Hello everybody, and welcome to the next video of the course. In this video I simply want to continue the material from last time where we introduced while loops. In this video I just want to show you some more examples of while loops just to get a sense of what they can do. In particular, loops are extremely powerful. Okay, so like modern computing is basically impossible without loops. There's no real way for me to give you a sense of that so early in the course, but as we progress through the course, you will see how powerful and how necessary loops are. So this is just sort of one more step in seeing what all loops can do for you. So the goal of this video is just to show you a couple more sophisticated examples of while loops. So I'll give you two more examples using them. These two examples are more sophisticated than what we did in the intro video. So example one, I want to build a factorial calculator. So first I need to introduce what a factorial is. So if n is any whole number, positive whole number, n exclamation mark, so you read that in English as n factorial, is this number. N, the number itself, times 1 less than that number, times 2 less than that number, etc., all the way down to 1. So 4 exclamation mark, 4 factorial is 4 times 3 times 2 times 1, right? Start at 4 and ladder your way down to 1, and you get 24 as the result. 5 factorial, start with 5, multiply your way down to 1, you get 120. So that's what a factorial is, and that's how it works. So what I want to do is write a program that lets the user enter a whole number, and the program calculates and then prints the factorial of that number to the screen. So the computer, right, you input 5, the computer gets that 120 number for you. Or you input the 4, and the computer prints that 24 number for you. Okay, so I want to build this in the compiler. Okay, so I've started here by just grabbing the n value from a user. You know, what number do you want? Okay, now let's think about how would you use a loop to calculate a factorial? Well, what you need to have happen is you have to start at n and then work your way down, multiply by n minus 1, then by n minus 2, etc. And you have to sort of iterate that process, right? So what I'm going to do is I'm just going to start with a number, factorial, that right now is 1, because I haven't multiplied anything yet. Right, so the factorial will, in the end, be n times n minus 1 times n minus 2, etc. But right now it's nothing, right? I haven't done anything. And then what I want to do is set up a loop like this, while n is greater than 0. Okay, so what I'm going to do is I'm going to start at n, and then after the loop code segment is done running, I'll knock it down to n minus 1, then knock it down to n minus 2, etc. So I'm going to fill in some code here in a second. Okay, but the loop is going to end like that. I'm going to knock down the n value by 1. And then what do I want to have happen inside this loop? What I want to have happen is factorial should be whatever the value was a second ago times whatever n is right now. Okay, so let's think about what's going to happen in this loop. So, or in this program. The user, let's say, hands 5 right there, right? So n is 5. Well, 5 is bigger than 0, right? No argument there. So I'll go into this loop. Factorial will be 1, its current value, 1 times 5. So on the first pass through of this loop, factorial has value 5. Then I knock down the value of n by 1. So now n has value 4, right? Well, 4 is bigger than 0, isn't it? So I'm going to do the loop again. Now recall, right, factorial has value 5. And what am I going to do? I'm going to replace it with value 5 times 4. Then knock n down by 1 to 3. Well, 3 is bigger than 0. Factorial now has value 5 times 4, or 20, right? And I'm going to replace it with that value times 3. Right, so let's just run this loop and let me, inside of it, let's print factorial. So I'm not done with the program yet, but let's just watch this loop in action. So on each pass through the loop, let's print what it thinks factorial is. So I'll give it a small n value, maybe 6. Okay, so when the loop first starts, I haven't changed the value of factorial, right? It was 1. And when I get to this point in the code, the first pass through the loop, that value is still 1. So it prints 1. Okay, then, after I do that printing, factorial is its old value times the n value, which is 6. Then I knock down the value of n by 1, right? Then I restart the loop. When I restart the loop, the factorial value is 6, right? And then I do my thing again, and now I do 6 times 5. This here is 6 times 5 times 4, etc., right? So every pass through the loop, you're sort of tacking on something to the end of factorial to make it bigger. So let me now take this command out of the loop. And now, let me just, down here, print what factorial is. So your number factorial is, and just have it display that for me. Okay, so my n value, I'll start small, 4. Your number factorial is 24, what we expected it to be. Okay, let's run it again. What's your n value? 5. Your number factorial is 120, right? So it's doing what I want it to do. It's doing that calculation for me. So your actual calculator, like if you have a TI-80, whatever, TI-84, there's a exclamation mark button on there, and you can ask the calculator, what's 5 factorial? What is, maybe a little bigger, what's 8 factorial, right? 40,320. So how's your calculator doing that, right? When you enter that 8 and literally hit enter on the calculator, what is your calculator doing? Well, somebody has coded this algorithm inside of it. Right, so this lives somewhere inside your calculator, and that's how the calculator knows to print that number to you. Okay, so there's another example of using a loop. You can use it to calculate a factorial. Okay, let me show you one more example. A prime number checker. This is classic old school programming exercise here. Okay, this shows up in all sort of textbooks when you first introduce loops. So first, let's just remind ourselves what a prime number is. A positive number n is prime if its only divisors are 1 and itself. Okay, so that's a third grade definition or something that you may or may not have forgotten. So for example, 5 is prime. The only numbers that divide 5 are 1 and 5. 8 is not prime though, because 4, which is not 1 or 8, right? 4 is a divisor of 8. 2 is also a divisor of 8. So if you have just a single divisor besides 1 and yourself, you are not prime. So numbers like 2, 3, 5, 7, 11, 13, these are the prime numbers. Numbers like 4, 6, 8, 10, 15. Numbers like this are not prime. Okay, so what I want to do is write a program that, again, lets a user enter a positive number, and this time instead of calculating a factorial, I want the program to decide whether or not that number is prime. So if the user enters 5, the program should tell the user, hey, that's prime. If the user enters 8, the program should be able to tell the user that is not prime. Okay, so before I actually write the code, let me just point out that when you start writing more sophisticated programs, it's often helpful to sort of step back before you code anything and sort of sketch out a schematic of how the program will work. So this will be true of like pretty much any program from here on out. So at the beginning of a programming course, you typically are not writing what I would call sophisticated programs. There's not a whole lot to them, either in terms of the amount of code or the logical finesse that goes into them. Okay, but once you start writing bigger, better, more impressive programs, as we will be doing from here on out, basically, it's useful to not just start programming immediately. It's useful to sort of think through the logic of how you're going to teach the computer to do this task. And one thing you can always do is what I have written here. It's useful to think of how you, with just like paper and pencil, no computer, how would you do this task, right? So you have to teach the computer how to do this, right? You have to teach the computer how to detect whether or not a given number is prime. Well, if you're going to teach the computer that, then you, of course, yourself have to know how to do that, right? You can't teach somebody else something that you yourself don't know how to do. Okay, so that's what we're going to start by thinking about. So just imagine I hand you a number. That number could be 5, it could be 20,365,000,000, on and on, right? It could be any number. And I ask you, hey, I really need to know, is this number prime or not? What would you do? And the answer is, well, I haven't thought about that since second grade, so maybe I don't know what to do, right? But if you think about it for a while as to what it means to be prime, and if you play with some concrete numbers, you can come up with a procedure for doing this without too much trouble. So let's think about the number 15, okay? So 15 is small, okay? We all know 15 is not prime, but let's just use it as a thought experiment. This number, suppose you don't know if it's prime or not, right? Well, that number is prime if and only if it has a divisor besides 1 of 15. Sorry, let's just say the number is not prime, right? This number is not prime if and only if it does have a divisor, right? Sorry, not prime. So one thing you might want to do is just check, does it have any divisors besides 1 in itself? And you can just sort of think about iterating through these numbers. So like you could just check, is 2 a divisor? Is 3 a divisor? Is 4 a divisor? And so on up to 14. If you ever see a divisor, you know the thing is prime. If you never saw a divisor in that range, then you know it's not prime. Or sorry, you know it is prime, right? If you never saw a divisor, you know it is prime. So if I hand you 15, 15 is small. All of you, I think, can just divide numbers if you felt like it. So you can check, right? 15 divided by 2 is like 7.5, right? So 2 does not go into 15 evenly. 2 is not a divisor. But 3, right? 15 divided by 3 is 5 even, right? 3 goes into 15 evenly. Oh, so you found the divisor, right? Didn't have to look very far, but you found one. As soon as you find the divisor, 15 is not prime, you can quit looking. So 15 is small. You can use the same process on any number, right? So if I gave you, say, 321 or whatever, right? One thing you could do is divide that number by 2. See if you get a whole number or not, right? Divide the number by 3. See if you get a whole number or not, etc., right? Now, I'm not claiming this is the only way to check if a number is prime, but I'm claiming it's a way. So once we have this procedure outlined in our minds, we could ask ourselves, do I have the tools at my disposal right now in this programming course to implement this algorithm I just outlined? And in this case, the answer is yes. But anyway, before we jump to the code, here is sort of a schematic, or what I call pseudocode. It's a sketch of how the program will work. So this is code-ish, right? Python won't literally be able to do this for you, but you can translate this into Python if you want to. So the program starts by getting the number from the user, and then x here is going to be the number I'm starting at to check for divisors. Just like with 15, you don't want to start at 1 because you don't care about 1. You care about numbers besides 1 and 15. So I'm going to start at 2, and then notice at the end of this loop, x increases by 1. So x is just kind of like a dummy variable whose only purpose is to be all these intermediate numbers for my divisor checks. Okay, so I start x at 2. I will check whether or not x is divisor of the number the user gave me. So we can talk about how to check that in a second, but that's what you need to do, right? So x starts at 2, so you need to check. Is 2 a divisor of number? Well, if it is, right? If x is a divisor, then you can just like stop the loop, right? You don't need to keep going and just record that this number that the user gave you is not prime, right? And then increase x by 1. So if x wasn't a divisor, you have to keep looking, don't you? Right, so then x would need to click up to 3, check if 3 is a divisor. If 3 is a divisor, stop the loop. But if 3 is not a divisor, click x up to 4, x up to 5, x up to 6, etc. So just keep going until you've exhausted the range of possible divisors, right? So once you reach 15 in this case, right, you don't look anymore. So that's how the program is going to work. So some of these lines of pseudocode here are actual code, right? X equals 2, x plus equal 1. But things like this, the heart of the loop, we're going to have to translate that into Python. Okay, so let's go to Python and see. Okay, so I can wipe out this. I still need to get the number from the user. Maybe I can just call it number here, right? If I want to. Okay. So now I need to check whether or not the number is prime. Okay, and so probably the most, I don't know what the word is, elegant, or the most common way you'll see this kind of program written is to use what's called a Boolean variable. So at this point in the course, we don't have this concept, but we do have the concept of like a numeric variable or a string variable. So a variable, right, can take on a numeric value. It can be a sentence, be a string value, right? There are other types of variables, though, that can take on other types of values. And let me just show you one right now. Okay, so you see how this word true lit up in purple? That's a reserved word in Python. So what I've done here is I've created a variable called prime. So there's like a place in memory, a box, right? And in that box, I'm going to put a value. But that value is not going to be a number. It's not going to be a string. It's going to be the value true. Okay, so a Boolean variable is a variable that can only take on one of two values, can either be true or false. Okay, so it's kind of like a Boolean expression, right? A Boolean expression can either be true or false. A Boolean variable is simply a variable that's either true or false. Okay, so this is not a number, right? And this is not the string, right? So I could put quotes around this and make it like the word true, but that's different, right? The word true is just one of many words, right? But I'm talking about the actual value of true. Okay, so what's happening here is number is whatever it is. I don't know what the number is, right? The user gave me 5. They gave me like some number bigger than the number of atoms in the universe or something. Who knows, right? But I'm going to default to thinking that that number is prime, okay? And then in the pseudocode sketch I've outlined, right, I'm going to check if something's a divisor or not. And if it is a divisor, then I can change the value of that Boolean variable to false. Right? So I'll assume that the number is prime, and then I'll go looking to prove myself wrong. Okay, so now let me just copy what I have from the slides, right? Yeah, there we go. Okay, so from the slides, the next thing we have to do inside this loop is check whether or not the current x value is a divisor of number, right? Now, how do you do that, right? Well, the answer is you have to take number, divide by x, and see if you get a remainder or not. Or I guess to be more precise, see if you get a remainder of 0. Okay, so suppose this number is 6. 6 divided by 2 is 3 with 0 remainder, right? So in other words, for 2 to be a divisor of you, the number, right? When I divide you by 2, the remainder must be 0. That's what it means for you to be a multiple of something, or for, in this case, 2 to be a divisor of you. So all that to say, if you want to check whether or not 2 or 3 or 4, whatever, is a divisor of number, you have to take number, divide by x, see if your remainder is 0 or not. Okay, so how do you do that? Well, the answer is we have an operation, the percentage symbol, remember, right? The percentage symbol will tell you what a remainder is when you divide something by something. So I'm going to take number, divide by x, and see if my remainder is 0 or not. All right, so if, when I take number and divide by, starting with 2, right? But whatever the value of x is, right? If I take number, divide by 2, the remainder is 0, what does that mean? It means you found the divisor, right? So this number actually wasn't prime. I've proven myself wrong, and then I can stop the loop. Okay, so the loop is now actually done here. But let's just, again, talk through what's happening. Let's say that number here is 15, right? Let's say number is 15. Well, x is 2. 2 is less than 15, so I go inside the loop. 15 divided by 2 does not have remainder 0. Right? 15, when you divide it by 2, there's stuff left over because 15 is not a multiple of 2. So I don't even see this if statement, right? I just skip right over it. And then what I have to do, right? I have to increase the value of x by 1 to now increase x to 3. Okay, so now I check. 3 is still less than 15, right? But now 15 divided by 3, oh, that remainder is 0. So now I record this Boolean variable here as false instead of true. I change the value of what's inside that box, and then I can stop the loop. So here's a loop that can just sort of one by one check all of your possible divisors. If you ever see one, and you only have to see one, right? You only have to see one divisor that's not one in yourself. then you'll break out of the loop and record that you saw that divisor. So now at the end here, if I want to actually print things, I can do something like this. If prime is still true after all that. Right? I assumed prime was true up front. I assumed I had a prime number, and then I just sort of proved myself wrong sometimes, right? So if the value of prime is still true, then I should tell the user, right? You gave me a prime number. Else, not prime, whatever. Okay, so this program should work. I guess I should say I never really know till I run it, you know. So let me put in a number we know is not prime, 10. It's told me not prime, right? Because what happened, presumably, right? X started at 2. 2 is less than 10. I went into this loop, right? 10 divided by 2, oh, that remainder is 0, right? Because 2 is a divisor of 10. So prime was false. I break out of this, right? Therefore, I don't go into this if statement here. I go into this else. Okay, let's do it again with a different in value. How about something we know is prime, 7, right? Tells me you gave me a prime number. Why is that, right? Well, because prime was initially set to true. And what did I check? I checked 2, 3, 4, 5, 6. I checked all those numbers, and I never once got a divisor hit, right? This condition was never satisfied. Therefore, I never changed the value of prime. Therefore, I never broke out of the loop or I never broke out this way, right? Therefore, when the loop finally terminated, because x got too big, right? X finally reached 7, so the loop stopped. After the loop was done, prime was still true. Right, so I go into this. Let's do a couple more for fun. Let's enter a bigger number. Okay, so 5, 4, blah, blah, blah. This is big, right? And I know this is not prime, this number, because it's even. So 2 is a divisor, right? Let's just see if it does. Yeah, so not prime, right? Okay, one last little note on this program. You actually don't have to have this break statement here. So you could take this out and the program would give you the same result. The only reason I have this here is for efficiency's sake, okay? Because again, if you find a single divisor, you don't have to keep looking, right? This loop is a searching loop. It's trying to see if you have a divisor or not. Once you find a single hit, you can stop. So if you take this break statement out, all that means is that this loop will just keep running, keep running, keep running, but prime will still be false. You're just going to keep finding perhaps more divisor hits, so you're just going to keep learning that prime is false. You're going to learn that a bunch of times maybe, right? So anyway, from a logic standpoint, you don't need this. This is here from an efficiency standpoint, right? So with a number bigger like this, right, this loop actually stopped on the first iteration because that number is even, right? So anyway, sometimes you write things in the code not because they're strictly logically necessary, just for efficiency's sake, or even elegance's sake, right? You don't want to. It's considered more elegant to make the computer do as little work as possible. And so, by the way, this program, as I've written it, is actually not the most elegant or efficient program for this. You can think about how I have not done something efficient here if you want to. Okay, so that's the end of this video, the conclusion. Hopefully seeing these two examples has been helpful to you, in particular this sort of talking out loud or talking with your partner maybe, right, about how would I do this task, right? This writing a program that does this thing here, this prime checker, that seems harder to me than like, you know, writing a program to calculate a numeric grade just given some exam grades or whatever, right? This kind of program, I don't think you can just sit down and start writing, especially if you don't have much programming experience. So this kind of thought exercise where you really think through, how do I do this, right? How would I perform this task? Really thinking through what the algorithm is or what a procedure might be before you start coding. That's actually extremely useful, and I would suggest that you use it almost always if you're writing a program that's more sophisticated.